It seems that new, unprecedented discoveries about our universe are being announced on an almost daily basis. Astronomers are identifying new planets and even whole planetary systems with such speed that simply cataloging these findings has become a challenge. The news is constantly filled with reports of strange new worlds, novel cosmic properties, and fresh reasons to be amazed by the cosmos. But I want to take this sense of wonder a step further and invite you to think about the living things that might share our galaxy and the entire universe with us. Just imagine for a moment that alongside the familiar plants and animals of Earth, countless other unknown life forms exist on these newly found worlds. To begin this journey, let's start with some simple mathematics. Our galaxy contains far more planets than it does stars, which is not particularly astonishing when you consider the scale. The Milky Way is home to roughly 300 billion stars, an almost incomprehensible number. Yet even a single star, our own Sun, governs a system with over 100 planets, moons, and sizable asteroids. Given that each of these celestial bodies has unique properties, and many could harbor organisms, if this arrangement is typical, then our galaxy likely holds about 30 trillion such objects. Numbers of this magnitude are typically reserved for astronomy or perhaps discussions of national economies. Out of those 30 trillion potential worlds, we have so far located fewer than 4,000, which represents an infinitesimal fraction of the total. Yet even within this tiny sample, the variety of planets we've found is breathtaking. We know of worlds that orbit inside their star's atmosphere, planets completely submerged in water, and rogue planets that wander starless through the frozen emptiness of space. One can only imagine what other marvels await discovery as our instruments grow more powerful. Numbers of this magnitude are typically reserved for astronomy, or perhaps discussions of national economies. Out of those 30 trillion potential worlds, we have so far located fewer than 4,000, which represents an infinitesimal fraction of the total. Yet even within this tiny sample, the variety of planets we've found is breathtaking. We know of worlds that orbit inside their star's atmosphere, planets completely submerged in water, and rogue planets that wander starless through the frozen emptiness of space. One can only imagine what other marvels await discovery as our instruments grow more powerful. This sheer volume of worlds leads to a rather startling conclusion. I want you to picture the most bizarre planet your mind can conjure, something entirely different from anything yet discovered. Perhaps this world has an unusually high concentration of a rare element, like terbium. Or maybe it's the moon of a rogue planet, adrift in perpetual cosmic night. You could even imagine a planet much like our own, teeming with life on its continents and in its oceans, but based on an entirely different chemical foundation. Your world could be truly fantastic, with an average density less than water or a composition of pure iron. Now, let's assign a probability to your imagined world, say 1 in a million, which is about your chance of being struck by lightning this year. Even with such remote odds, you can be confident that approximately 10 million such planets exist in our galaxy alone. If you make the probability even slimmer, just 1 in a trillion, our galaxy would still contain around 10,000 of these worlds. This means that no matter how strange a planet you envision, as long as it conforms to the laws of physics and chemistry, something very much like it almost certainly exists. This is the core idea I want to convey. The number of planets in the Milky Way is so immense that any conceivable world that is physically possible has a strong likelihood of actually existing somewhere within it. And if those figures don't leave an impression on you, just recall that our universe contains billions of other galaxies, each of which probably hosts a similar planetary census. What, then, does this imply for the existence of life? With such an extraordinary assortment of planets, we should anticipate an equal, if not greater, variety of life forms. This very concept, however, presents a significant challenge for us. We are only acquainted with a single type of life, our own, which is based on carbon chemistry and depends on liquid water. All biological diversity on our world essentially stems from one experiment carried out in just one of the universe's countless laboratories. Consequently, our planet and its rich biosphere offer little guidance when we try to establish benchmarks for the sheer complexity and variation that life in the galaxy might exhibit. Despite this limitation, the knowledge we have of Earth-based life is our only starting point, so we must make the most of it. Our exploration into the potential forms life could adopt throughout the galaxy will start by defining what I'll call the rules of the game, the core principles that have sculpted life here into its current state. I would argue that the most crucial of these principles, evolution through natural selection, is likely to be a universal force operating under almost any conditions imaginable across the cosmos. A second major principle, carbon-based chemistry, is probably not as universal, but it provides a familiar framework to begin our analysis. For the purpose of this discussion, we will sort all potential life into three distinct categories. Life that is similar to ours, life that is somewhat different, and life that is completely unlike anything we know. We will concentrate most of our efforts on the first category for obvious reasons. Once we have established the fundamental rules for investigating the probability of life similar to our own emerging and surviving, we can then explore what outcomes these rules might yield in the diverse environments of our hypothetical exoplanets. First, let's consider a planet within the habitable zone. This is a terrestrial world orbiting its star at a specific distance that permits liquid water to persist on its surface for long stretches of time. Evaluating the conditions on such a planet is a relatively straightforward starting point, as we have the extensively studied example of Earth. Many recently found exoplanets fit this description, including the world-circling Proxima Centauri, our Sun's nearest stellar neighbor, and 3 of the 7 planets in the TRAPPIST-1 system, all of which are positioned where surface water could remain stable. Another possibility is a planet with a subsurface ocean, where vast bodies of liquid water are sandwiched between a solid rocky mantle and a thick, overlying shell of ice. You don't have to look far to find such worlds, as they exist right here in our own solar system. Geologists believe that hidden oceans can be found on Pluto and on several moons orbiting the outer gas giants, offering tantalizing prospects for life sheltered from the harshness of space. A far more solitary type of world is the rogue planet, a celestial body that has been ejected from its original solar system and now drifts through the vast emptiness of interstellar space. These cosmic wanderers are not automatically condemned to be frozen and inert. Like other planets, they can possess internal heat sources, and the energy flowing from their cores is entirely unaffected by the lack of a parent star's light. Imagine a water world, a planet with no land masses whatsoever, where the entire surface is a single, uninterrupted ocean. The defining characteristic of such a realm would be the distinct stratification of water at various depths. On Earth, these layers are primarily determined by temperature and salinity. But on an exoplanet, immense pressure could be the dominant factor. This opens up fascinating possibilities, such as different forms of life evolving independently within each layer, leading one to imagine epic conflicts between civilizations of the deep and the surface. Then there are planets in synchronous rotation, which are tidally locked to always present the same hemisphere to their star, just as the Moon does with Earth. A great number of the exoplanets we've found, including those in the TRAPPIST-1 system, are thought to be of this type. The unique geography of these worlds is defined by extremes. One side is eternally scorched by the star, while the other is trapped in perpetual, freezing darkness. Life could potentially thrive only in the twilight zone, the narrow strip of land separating the fire from the ice, where powerful winds constantly transfer heat from the hot side to the cold. Let's now turn to the super-Earth, a rocky planet larger than our own, but smaller than Neptune. The universe seems to be teeming with worlds like this, which makes our own solar system's lack of one somewhat unusual. Given their significant mass, the most defining environmental factor on a super-Earth would be its intense gravity. For any creatures living in the depths of its oceans, this crushing force would be of little consequence, but any life that ventured onto the land would need to develop sophisticated strategies to cope. On our world, with its more forgiving gravity, life has devised countless solutions. Plants use capillary action, insects rely on exoskeletons, and mammals have internal skeletons. But what kind of adaptations might arise if Earth's gravity were twice, or even 10 times as strong? Could a reptile, for instance, evolve a fish-like swim bladder to offset the immense gravitational pull, eventually developing into a flying dragon, capable of navigating the dense atmosphere of such a massive planet? By exploring these kinds of scenarios, you and I can start to move beyond our initial, somewhat fixed and inflexible view of the cosmos. It allows us to entertain the idea of life that is fundamentally different from our own. We can approach this process systematically, setting aside the familiar biological traits we often assume are universally necessary for life to exist. What if we entertained the notion of life founded on something other than carbon? Silicon, for instance, sits directly beneath carbon on the periodic table and shares many of its chemical properties. This similarity has made silicon-based life a recurring theme in science fiction for many decades. A classic example comes from a 1967 episode of Star Trek titled The Devil in the Dark, where miners on a remote planet disturb the Horta, a species of rock-dwelling silicon-based organisms that are at first hostile. We will delve into the types of planets where such beings could potentially emerge and explore the profound questions they raise. For instance, would you even be able to identify such creatures as being alive if you encountered them? Is it possible that we would perceive silicon-based life forms as nothing more than inanimate rocks? The further we stray from biological models that are familiar to us, the more challenging it becomes to find clear answers to these kinds of questions. Life might even be constructed from elements that are scarce on Earth but abundant elsewhere in the cosmos. Scientists have recently begun to embrace this conclusion, following a study that cataloged the diverse chemical compounds present in other stars, which are presumably also found in their orbiting planets. This suggests a much wider palette of potential biochemistries is available throughout the universe. If we truly allow our minds to wander, we can begin to picture all manner of life forms that bear no resemblance to our own. Life that isn't based on chemistry, or even life that doesn't operate under the principles of natural selection. Ultimately, this brings us to the central question that drives our curiosity. Given the astonishing variety of both discovered and theorized exoplanets, Should we expect to find a comparable level of diversity among the life that may inhabit them? Our entire exploration into the possibility of life arising beyond Earth is grounded in two overarching principles. These same two principles also establish the limits of our investigation. The first of these is the understanding that the physical universe operates according to a relatively small set of universal laws. A second core principle is that the laws of physics observed here on Earth are constant and universal, functioning identically in every corner of the cosmos and throughout all of time. These concepts are so deeply ingrained in a scientist's mindset that they form the very basis of our education and worldview. Anthropologists might describe them as basic beliefs, ideas so fundamental to a group that they are accepted without a second thought. However, I have come to understand that these core principles are not commonly held or seen as self-evident by everyone. It is not that people disbelieve them. It is more that when considering vast topics like extraterrestrial life, these rules are not automatically part of the thought process, which is why this chapter is dedicated to exploring them. We are about to explore the essential laws of physics and chemistry that will serve as our guide in considering the possibility of life beyond Earth. We will begin with the principles governing the world you experience every day, which involves ordinary-sized objects moving at typical speeds. This domain is governed by what we call classical physics, a framework that can be pictured as three great pillars supporting our entire understanding of the physical world. Let's examine these foundational laws before we proceed to more complex fields of study. The initial framework of laws that explains our everyday reality was established by the English scientist Isaac Newton, focusing on the movement of physical objects in a field known as mechanics. This subject has captivated physicists since antiquity, with thinkers as far back as ancient Greece attempting, and largely failing, to create a complete model of motion. Newton's breakthrough came from inventing a novel mathematical tool, what we now know as differential and integral calculus, which enabled him to finally articulate the principles governing the trajectory of any object moving through the air. What we refer to as Newton's laws of motion are surprisingly straightforward. The first states that an object's velocity stays constant unless an external force intervenes. The second law explains that an object's acceleration is directly linked to the force applied to it and inversely related to its mass. Finally, the third law posits that for every action there is a reaction of equal magnitude and opposite direction. Crucially, these principles apply universally to all moving things, a concept we will revisit. The first two laws essentially provide a framework. One tells you how to identify a force at play, and the other describes its effect, though they do not specify what natural forces exist. With that in mind, let's turn to the forces that direct the movements of planets, which leads us to what is arguably Newton's most famous discovery, the law of universal gravitation. This principle establishes that any two objects in the cosmos pull on each other with a gravitational force. This force's strength is determined by multiplying their masses and is weakened by the square of the distance separating them. To put it simply, doubling an object's mass also doubles the gravitational pull, but doubling the distance between two objects reduces their mutual attraction to just 1/4 of its original strength. Newton himself would likely have been astonished to learn that his laws would eventually enable us to calculate the mass of planets circling stars that are trillions of miles away. As we will explore further in Chapter 5, a primary technique for finding these exoplanets is to watch for the subtle dip in a star's brightness as a planet crosses in front of it, a process called a transit. By timing these transits, we can apply Newton's principles to determine the planet's orbital distance. When we merge that data with the star's known temperature, we can begin to address profound questions, like whether liquid water could persist on the planet's surface, which in turn lets us speculate about the chances for life elsewhere. It is safe to say that those living in Newton's time could not have foreseen how his laws would be used centuries later. But the impact of his cosmic perspective goes far beyond just finding new planets. The rise of Newtonian mechanics truly established the groundwork for all of modern science. It set the very paradigm for how science operates, making theoretical predictions about undiscovered phenomena, and then rigorously testing those predictions against real-world evidence. In many ways, every technological advancement our civilization enjoys today can be traced back to this Newtonian method of investigating the natural world. Taking this idea a step further, you can imagine the Newtonian solar system as an intricate and precise clockwork mechanism. The planets orbit with the regularity of a clock's hands, all guided by laws that function like perfectly meshed gears. Projecting this analogy onto the entire cosmos reveals a universe that is fundamentally orderly, consistent, and predictable. A grand machine where unexpected deviations cannot occur. For instance, the flying dragons mentioned in the last chapter could only ever achieve flight if the upward force from their unique bladders was strong enough to overcome the planet's gravitational force, a non-negotiable physical constraint. A fairy's capacity for flight would be a delicate balance between the lift generated by her wings and her own body weight, because even in magical tales, Newton's laws hold true. This perception of the universe as a finely tuned mechanism extended well beyond the natural sciences, and indeed beyond science altogether. Some historians even propose that Isaac Newton's work directly influenced the creation of the Constitution of the United States, arguing that the Founding Fathers were inspired by his discovery of universal laws to formulate principles for an ideal society. However, as you will soon discover, the 20th century would shatter these notions of inherent order and predictability in nature. Yet, before scientists reluctantly set this idea aside, it served as the foundation for the development of two other critical scientific fields. These domains, electricity and magnetism, are the other pillars that will support our ongoing exploration of life on exoplanets. And they also grew from the concept of a clockwork universe. Humanity has been familiar with electricity and magnetism since antiquity, from the static cling that bonds wool socks together after tumbling in a dryer, to the magnetic force that holds decorations to your refrigerator door. The ancient Greeks viewed electricity as an intriguing natural occurrence, and were even aware that electric charge existed in two forms. We now label them positive and negative, understanding that opposite charges attract, while similar charges push each other away. For centuries, though, this was the entire scope of human knowledge on the subject, as static electricity offered no practical applications. Magnetism, on the other hand, was a completely different story. Primarily because people soon found naturally occurring magnets in the form of iron oxide, which you might know as magnetite or lodestone. Numerous legends surround the discovery of these natural magnets, with one tale crediting a shepherd named Magnus, from whom the term magnetism supposedly originated, after he found that the iron nails in his sandals stuck to the rocks. Legends aside, these natural magnets possessed a single, profoundly useful characteristic. Fragments of magnetite consistently orient themselves along a north-south axis, making them perfect for use as a compass. This tool proved to be exceptionally valuable, enabling people to navigate through completely unknown territories and becoming essential for sailors on the open ocean or for caravans journeying across deserts. Simple lodestone compasses were already in use in China as early as the 1st century BCE, and later, during the 9th and 10th centuries CE, the Vikings relied on them for navigating at sea. Subsequent investigations into electricity and magnetism uncovered two essential properties. The first was identified by William Gilbert, an English scientist and court physician to Queen Elizabeth I, born about a century before Newton. He established that magnetic poles are never found in isolation. The second came from Charles Augustin de Coulomb, a French scientist born nearly a decade after Newton's death, who demonstrated that the force between electric charges could be captured in a simple equation remarkably similar to Newton's law of universal gravitation. This was the state of knowledge as the Industrial Revolution began, with most people perceiving static electricity and magnetism as entirely separate phenomena. The insight that connected them emerged, as it so often does in science, from technological innovation. The Italian scientist Alessandro Volta developed a device he named the electric pile, which you would recognize as a battery. This invention was significant because it produced moving electric charges, thereby creating what we now call an electric current, a completely new manifestation of electricity. The conceptual wall separating electricity from magnetism finally began to crumble during a physics lecture in Copenhagen. The speaker, Danish physicist Hans Christian Ørsted, was demonstrating Volta's new invention to his students when he observed that the needle of a nearby compass twitched every time the battery generated a current. This was the first proof that moving electric charges produce magnetic effects, establishing an undeniable link between electricity and magnetism. You have likely already made use of the consequences of Ørsted's discovery multiple times today, without giving it a second thought. His observation led directly to the invention of the electric motor, so every time you press a button to raise a car window or turn on a blender to puree tomatoes, you are benefiting from that breakthrough. Decades later, the English physicist Michael Faraday supplied the final piece of this scientific puzzle. Faraday discovered that altering the magnetic field in the vicinity of a wire, for instance, by moving a magnet through a copper loop, causes an electric current to flow, even if the wire isn't connected to any power source. We can therefore condense our discussion into four fundamental principles. First, opposite electric charges attract each other, while like charges repel, which is Coulomb's law. Second, magnetic poles never exist in isolation. Third, moving electric charges create magnetic fields. And fourth, changing magnetic fields induce electric currents. In the realm of electricity and magnetism, these four statements, when expressed as formulas, are as foundational as Newton's laws are to mechanics. These principles provide a complete account of everything we understand about such phenomena. This returns us to a point where a few concise and simple laws can describe a multitude of complex natural events. As we explore the potential for life on exoplanets, we will frequently circle back to these established principles of electricity and magnetism. These principles provide a complete account of everything we understand about such phenomena. This returns us to a point where a few concise and simple laws can describe a multitude of complex natural events. As we explore the potential for life on exoplanets, we will frequently circle back to these established principles of electricity and magnetism. These principles provide a complete account of everything we understand about such phenomena. This returns us to a point where a few concise and simple laws can describe a multitude of complex natural events.
As we explore the potential for life on exoplanets, we will frequently circle back to these established principles of electricity and magnetism. These principles provide a complete account of everything we understand about such phenomena. This returns us to a point where a few concise and simple laws can describe a multitude of complex natural events. As we explore the potential for life on exoplanets, we will frequently circle back to these established principles of electricity and magnetism.
For instance, in Chapter 13, I will explain how coronal mass ejections, which are immense bubbles of ionized gas erupting from the Sun, can influence a planet's biosphere. The principles of electromagnetism precisely describe their creation and trajectory. These events are so powerful they could dismantle a highly advanced technological civilization like our own in a matter of hours. We will also examine why Mars, unlike Earth, has no magnetic field, which permits solar radiation to strike its surface directly and likely eradicate any life that might exist there. The laws of electricity and magnetism become particularly crucial when we consider the emergence of life forms entirely different from our own. The interplay of electric and magnetic fields gives us a framework to define and characterize the level of complexity we see in life as it adheres to the laws of chemistry. Their ultimate significance, however, is that they represent the most vital tool in our search for life throughout the cosmos, allowing us to identify the limitations nature places on the origin and evolution of life on distant exoplanets. The principles we've outlined are collectively known as Maxwell's equations, after the Scottish physicist James Clerk Maxwell. Although Maxwell himself did not discover any of these individual laws, he was the first to grasp that they constitute a unified mathematical framework that links electricity and magnetism. As one of the preeminent mathematicians of his era, Maxwell's work delved into advanced fields we now refer to as partial differential equations and vector analysis. When he applied these mathematical tools to the four laws of electromagnetism, he uncovered a result that was nothing short of astounding. His equations logically demonstrated that accelerating electric charges must radiate specific kinds of waves. These waves, in turn, would be composed of oscillating electric and magnetic fields, propagating through space at a velocity dictated by the forces between electric charges and magnetic poles. Since the strength of these forces was already known, their speed could be calculated. Maxwell must have been astonished when he determined the numerical value for this velocity, as it proved to be equal to the speed of light, roughly 300,000 kilometers per second. This revealed that light itself was just another type of electromagnetic radiation. Consequently, a sock sticking to a towel, a magnet pinning a list to your refrigerator, and your very ability to read this text are all interconnected manifestations of the same fundamental physical force. And the revelations didn't stop there. Visible light is made of waves with lengths spanning from about 4,000 to 8,000 atoms. However, Maxwell's equations suggested that other forms of electromagnetic radiation with different wavelengths must also exist. By the close of the 19th century, an entire family of these waves had indeed been identified, beginning with radio waves and followed by other segments of the electromagnetic spectrum. This spectrum includes microwaves and infrared rays, which have longer wavelengths than visible light, as well as the shorter wavelength ultraviolet rays, X-rays, and gamma rays. It was also discovered that, as the wavelength shortens, the energy conveyed by the wave intensifies. In simple terms, if you take a wave of visible light and stretch it out, you get a radio wave. If you compress it, you get an X-ray. Electromagnetic waves are the source of most of the data we can gather about exoplanets, traveling to us at the speed of light. Each radiation type illuminates a particular phenomenon or a set of them. X-rays, for example, uncover events of immense energy release, while infrared radiation informs us about processes occurring at much lower temperatures. Yet, nearly all of these rays, with the exception of radio waves and visible light, are blocked by Earth's atmosphere, which is why much of our essential scientific data comes from instruments aboard satellites orbiting our planet, supplemented by observations from ground-based telescopes. Therefore, electromagnetic radiation, whose existence was first predicted by Maxwell's equations, serves as our primary instrument for investigating conditions on exoplanets. We will delve into this topic more deeply in Chapter 5, where the focus will be on the search for life beyond our solar system. The final pillar upholding the structure of classical science is thermodynamics, a name derived from the Greek roots thermo for heat and dynamics, the science of motion. Thermodynamics, as a scientific discipline, is concerned with the transfer of heat and, more generally, the movement of other forms of energy. Much like mechanics, electricity, and magnetism, our understanding in this area can be distilled into a small set of fundamental laws. We will primarily concern ourselves with two of them, the first and second laws of thermodynamics. The first law states that different types of energy can be converted into one another, but the total energy within an isolated system must always remain constant. The second law posits that, within an isolated system, the amount of entropy, which is a measure of disorder, can either increase or stay the same over time, but it can never decrease. The first of these laws is profoundly important for understanding the universe, as it establishes that energy can neither be created nor destroyed. It can only transition from one form into another. It is therefore useful to conceive of the energy that powers life, whether on Earth or any other exoplanet, as a continuous flow. This energy originates from a source, in our case the sun, then passes through the biosphere, and is finally released back into space in the form of infrared radiation. For every hypothetical instance of extraterrestrial life we examine in this exploration, one of our first actions will be to calculate and analyze all potential sources of energy. In most scenarios, the primary energy source will undoubtedly be the parent star, but other possibilities are certainly on the table. Here on Earth, we know of entire ecosystems that thrive independently of the sun, clustered around deep-sea vents on the ocean floor, which are powered by thermal and chemical energy from the planet's interior. It is highly probable that similar structures could exist on exoplanets, an idea we will return to when discussing life forms unlike our own. The second law of thermodynamics will prove to be of fundamental importance as we work to define the concept of life itself. The core issue is that any living system, regardless of its makeup, must maintain a state of high organization. The second law directly confronts this matter of order, establishing a universal rule. If you generate an ordered system like a living being in one location, you must compensate by increasing the disorder, or entropy, everywhere else. In essence, the classical Newtonian worldview holds that the universe functions according to 9 natural laws, 3 governing mechanics, 4 for electricity and magnetism, and 2 for thermodynamics. This perspective implies that every event in the cosmos can ultimately be described by a set of equations compact enough to fit on a t-shirt. Yet, for all its elegance and appeal, this depiction of the universe is ultimately too simplistic. This leads to the realm of modern physics. It is often claimed that the great discoveries of 20th century physics, relativity and quantum mechanics, demonstrated that the Newtonian framework was fundamentally incorrect. I must categorically disagree with this view. The Newtonian model of the universe is built on experiments involving objects of a normal scale, moving at normal speeds, and within that context, it works perfectly. The new physics simply expanded the scope of scientific inquiry far beyond those conventional limits. Relativity, for example, describes objects traveling at speeds approaching that of light or possessing immense mass, while quantum mechanics explores the universe at atomic and subatomic scales. However, if you apply the principles of either field to everyday objects moving at typical velocities, their laws converge to the familiar Newtonian ones we've already outlined. This is why engineers designing highways and bridges still rely on a thorough understanding of Newtonian mechanics. At most, these new fields of science can contribute a few additional principles to the magnificent 9 already established. Relativity, for instance, is founded on the core tenet that the laws of nature are the same in all frames of reference. While we will seldom return to this theory, it plays a vital part in the search for rogue planets, those that wander through interstellar space alone, a topic we will investigate later. Quantum mechanics operates very differently from relativity. Within an atom, physical events unfold in a manner that is completely alien to our everyday experience. In this quantum domain, nothing is fixed or continuous. Instead, nearly all phenomena are interconnected and mutually influential. Though scientists have yet to agree on a single interpretation of this bizarre field, we need only incorporate a few of its general principles into our list of universal laws. For our purposes, the most significant discoveries in quantum mechanics are those that clarify how atoms emit and absorb light. Unlike planets circling a star, electrons cannot exist in just any orbit around a nucleus. Their options are restricted to strictly defined energy levels. An atom releases electromagnetic radiation, including visible light, when an electron transitions from a more distant orbit to one that is closer. The opposite is also true, as an atom absorbs radiation when an electron moves from an inner orbit to an outer one. The frequency of this radiation, which corresponds to its color in the visible spectrum, is dictated by the energy difference between the initial and final orbits. Since the configuration of these possible orbits is unique for the atoms of each chemical element, the spectrum of radiation an atom emits or absorbs functions as a kind of chemical fingerprint. This is the basis for the entire field of spectroscopy, a powerful tool that, as we will see, allows us to determine if the conditions for life might exist near other stars. Thus, our effort to understand the universe boils down to the search for a few universal laws, much like those we have discussed. The tremendous simplification of our worldview that began with Newton gives us hope that a similar clarity will emerge as we gain a better grasp of new areas of physics. This hope is what fuels modern physicists in their pursuit of what is sometimes humorously called the theory of everything. This ideal, a single equation from which all known and yet to be discovered principles could be derived, would explain everything. Of course, we are a long way from such a theory, and many scientists doubt it can even exist. Furthermore, it is entirely unnecessary for our search for extraterrestrial life. But it is fascinating to imagine what future technologies, born from the achievements of a theory of everything, might look like. Our investigation into extraterrestrial life is shaped by a crucial concept called the Copernican principle, named after the Polish cleric Nicholas Copernicus. He became renowned for devising a mathematical framework for the solar system that placed the sun, not the Earth, at its center. This paradigm shift was the initial move on a long path to grasping a truth we now find obvious. Our home planet is in no way special or unique. It is simply a rocky world orbiting a common star in a nondescript area of a similarly ordinary galaxy, one among billions that exist in the observable universe alone. For some, this perspective on the cosmos is profoundly unsettling, as they feel it diminishes the significance of humanity. I, however, prefer to view it as a critical advancement on our journey toward knowledge. For me, accepting our planet's ordinary status brings with it a valuable insight. It means the natural laws we uncover right here and now are universally applicable, holding true across all of space and for all of time. The ancient Greeks, who were the trailblazers of what would become modern science, held a vastly different conception of the universe. Their cosmology positioned the Earth at the very center of everything, granting it a special status separate from all else. According to their beliefs, all terrestrial matter was composed of 4 elements: earth, fire, air, and water. The heavens, however, contained a 5th element, known as ether or quintessence, and were considered a realm of perfection, where celestial bodies moved in flawless, circular paths. Consequently, the lunar craters and sunspots that Galileo observed through his telescope presented a direct contradiction to the established Aristotelian view. This meant the ancient Greeks operated with 2 distinct sets of natural laws, one governing Earth and another for the heavens. It was our old acquaintance, Isaac Newton, who dismantled this dualistic system. As the popular account has been passed down, Newton was walking in his family's garden when he witnessed an apple fall from a tree. Looking up at the sky, he saw the moon and began to ponder. He understood that apples fall because of Earth's gravity, a force that had been thoroughly studied by Galileo and his contemporaries. Newton also recognized that the moon's path was not a straight line, but a circular orbit around the Earth. Applying his first law of motion, he deduced that some force must be continuously acting on the moon to maintain this orbit, preventing it from flying off into space. This led him to ask a question that seems simple today, but required true genius to formulate back then. Could the force that pulls an apple to the ground be the very same force that holds the moon in its orbit? The answer, as we now know, is a definitive yes. Today, we have a clear understanding that the force Newton identified is one and the same, described by the law of universal gravitation. In essence, there is no distinction whatsoever between the gravitational pull of celestial objects and terrestrial ones. This insight served as the first concrete evidence for the Copernican principle, the notion that the laws of physics and chemistry at work on Earth are equally valid everywhere else in the cosmos. Since the 15th century, an enormous body of data has been gathered that only strengthens this assertion. We can analyze the light emitted by a specific atom in a laboratory on Earth and find that it is identical to the light from that same type of atom in a distant corner of our galaxy, or even in another galaxy entirely. We can also observe the radioactive decay of elements during supernova events in galaxies billions of light-years away, and find that the results perfectly match the decay of those same elements in our labs. All available evidence points to one conclusion: Earth is not an exception. The physical laws that govern our planet are the same laws operating everywhere else. It is also important to remember that when you observe a galaxy a billion light-years away, you are seeing light that was emitted a billion years ago. This means you are literally looking into the past. Yet, the mountain of evidence confirms that an atom from a distant galaxy a billion years ago behaves identically to the same kind of atom in our laboratories today, proving that the laws of physics and chemistry are constant through time. As I touched on previously, we have already learned a great deal about the conditions on exoplanets. We know that the fundamental laws of nature operate on these worlds just as they do here. This knowledge enables us to make educated guesses about the potential characteristics of life forms on these distant planets, while also placing necessary limits on our imagination. For instance, the flying dragon we envisioned earlier is a perfectly plausible creature, as its existence doesn't violate Newton's laws of motion. Its exotic appearance is merely a secondary detail. Essentially, only life forms that can be explained by the laws we know are considered possible. Now, equipped with this understanding, let's turn our attention to the principles that govern living systems themselves. This brings us to a fundamental question. What exactly is life? While you are likely confident you know what life is and would recognize it instantly, providing a precise explanation proves to be exceptionally difficult. What specific criteria define the phenomenon we call life? The primary challenge stems from the fact that life on Earth, the only example we have, is staggeringly complex and diverse. Furthermore, a vast chasm separates the living from the non-living, and any complete definition must account for and explain this divide. As you might imagine, contemplating the nature of life and how to define it is a pursuit with a history stretching back centuries. Aristotle, for instance, contended that every living thing is composed of a material body and an immaterial essence he called a soul. This concept eventually transformed into the belief that a non-physical vital force is precisely what separates the living from the non-living, an idea known as vitalism. The conviction that life's existence depended on some mysterious force remained unchallenged until the emergence of cellular and molecular biology in the 19th and 20th centuries. We now recognize that at the molecular level, living systems adhere to the very same laws of chemistry that govern the entire universe, though typically in a far more intricate manner. Nevertheless, the sheer variety of living beings on our planet complicates any attempt to create a straightforward definition of life. In fact, a significant number of modern scientists argue that a simple, universal definition is fundamentally unattainable. For the purpose of our discussion, it is enough to understand that there are three dominant strategies for tackling this problem. Definitions that list life's properties, those that describe life as a process, and formulations derived from the laws of thermodynamics. We will now explore each of these categories individually. First, let's consider the definitions that are based on listing the properties of life. Proponents of this approach assemble a catalog of attributes inherent to living organisms. According to this framework, anything possessing all, or at least a majority of these characteristics is classified as alive, while anything lacking most or all of them is considered non-living. A typical list, like one you might find in a biology textbook, generally includes the following abilities: adaptability, growth and development, self-regulation, metabolism, a cellular structure, reproduction, and irritability, which is the capacity to react to environmental changes. Of course, a consistent problem surfaces whenever such lists are compiled. The moment we finalize a comprehensive set of required properties for life, we inevitably discover examples of organisms that are unquestionably alive, yet lack one or even several of these traits. A mule, for instance, which is the offspring of a horse and a donkey, is certainly a living creature, but it is incapable of reproduction. The physicist Daniel Koshland offered an even more clever illustration. A single rabbit cannot reproduce and would therefore fail our test for being alive. But a pair of rabbits can, meaning that together they meet the criteria. One strategy to resolve this issue is to decide that an entity is alive if it fulfills most of the criteria, even if it doesn't meet every single one. This effectively adopts a legal principle known as the preponderance of the evidence. However, this solution immediately introduces a new challenge. You are then forced to determine which items on your list are negotiable and which are absolutely essential, creating fresh ambiguity. A compelling demonstration of the difficulties that arise from this principle can be seen in the search for life on Mars. When the Viking landers arrived on the surface of the Red Planet in 1976, hopes were high that they would discover signs of life. The mission's design included at least 4 experiments intended to find chemical evidence of Earth-like metabolic activity in the Martian environment. The fundamental logic of the Viking program was therefore based on a definition of life reduced to a single property, a metabolism similar to our own. However, as the data began to arrive, many researchers realized that the experiments could produce positive results even when analyzing clearly inanimate materials, such as when specific chemical reactions took place in the Martian soil. According to numerous scientists, the decades-long controversies over the Viking landers' findings are tied, at least in part, to the restrictive definition of life that was used to design the experiments in the first place. An episode of Star Trek, The Next Generation, powerfully highlights the flaws of defining life through a checklist when the android Data makes a case that fire could be considered a living entity. And why not? Fire consumes resources from its surroundings, processes them, and releases waste. It can grow, replicate, and react to shifts in its environment. In essence, fire meets most of the qualifications on our list, perhaps with the exception of self-regulation. Yet very few people would be willing to classify it as being alive. An alternative way to use lists to define life emerges from the growing science of ecology. Rather than scrutinizing the attributes of individual organisms, an ecologist might focus on how that organism integrates into the intricate web of relationships that constitutes its ecosystem. The most renowned example of this perspective is likely the Gaia hypothesis, introduced by ecologist James Lovelock. He proposes viewing the entire Earth, including both its living and non-living elements, as one single, massive organism. This hypothesis often suggests that the planet's diverse ecosystems cooperate to sustain a stable environment that is conducive to the flourishing of life, a concept embodied by the name Gaia, the primordial goddess and ancient mother of all life in Greek mythology. The Gaia hypothesis has frequently come under fire because Earth's actual geological past is replete with catastrophes, which seems to contradict the notion of our world being the product of a deliberate, systematic creation of ecological harmony. For instance, there were periods when the entire planet became a massive snowball, its frozen surface and oceans completely encased in ice and snow, a state that only the immense power of volcanic eruptions was able to reverse. Consequently, while we can't dispute that all terrestrial organisms are integrated into vast ecosystems, the ecological perspective merely adds another item to our checklist for life. To be alive, an entity must be part of such a system. This might hold true for life on Earth, but there is no compelling reason to assume this property is a requirement for life on exoplanets. The same logic applies to the idea that living systems must be composed of cells. Though we are accustomed to cellular life, we have no grounds to believe extraterrestrial life must share this characteristic. In essence, while most properties on the lists we've discussed are certainly typical of Earth's organisms, it is just as certain that extraterrestrial life has no obligation to conform to them. So, when we eventually venture out into the galaxy, we might carry our checklist as a precaution, but we shouldn't place too much faith in its utility during our search. This brings us to definitions centered on life as a process, which took a significant step forward in 1994. In that year, NASA decided to renew its search for life in the galaxy, and gathered a group of scientific experts to formulate criteria for this concept. Based on a suggestion from Cornell University astrophysicist Carl Sagan, they defined life as a self-sustaining chemical system capable of Darwinian evolution. This phrasing has since become known in scientific history as the NASA definition. Despite its clear geocentric bias, we will find this formulation remarkably useful when contemplating potential forms of life on exoplanets. The mechanism of Darwinian evolution is more commonly known as natural selection, and we believe this process is likely at work on the vast majority of exoplanets. On Earth, it functions like this. Every organism inherits genetic material from its parents, which shapes its characteristics. These traits, in turn, are a primary factor in determining if the organism will survive long enough to pass its own genetic material to the next generation. You've likely heard the expression, survival of the fittest. Over vast stretches of time, traits that enhance survival become more common within a population, meaning natural selection produces organisms that are exceptionally well suited to their environments. This is the very process that gave rise to the incredible diversity of life we observe on our own planet. However, just because all living things on Earth are products of natural selection, it doesn't necessarily mean that something not created this way cannot be considered alive. We will explore several scenarios of this kind in Chapter 16 when we examine life entirely different from our own. The NASA definition is fundamentally one of many attempts to characterize life based on the processes that bring it into being. It suggests that to know if something is alive, you must understand its origins. If an organism is the result of natural selection, this definition classifies it as living, effectively making natural selection a criterion for life itself. Other processes have also been put forward as defining characteristics of life, with one of the most compelling examples stemming from systems theory and the idea of emergence. In this framework, life is described as an emergent property of chemical systems. The easiest way to grasp emergence is through the analogy of a sand pile. Picture yourself adding sand one grain at a time. As the pile grows, the interactions within it become increasingly intricate, even though they are just forces between individual grains. Then, perhaps at the millionth grain, something new occurs. You add that single grain, and a cascade suddenly tumbles down one side of the pile. This avalanche is an emergent property of the sand grains, as one grain alone cannot produce 1/10,000th of an avalanche. You need the entire collection of 1,000,000 grains for the pile to shift. Proponents of this view argue that life is a similar kind of chemical avalanche. If you make a chemical system complex enough, it is highly probable that life will emerge. The primary challenge with this type of definition is that it demands a profoundly detailed and accurate understanding of how the system arrived at its present state. In Chapter 5, we will delve into the even greater difficulties we face when searching for signs of life on other planets, let alone trying to reconstruct its evolutionary history. even on Mars, where we can deploy landers and probes for direct analysis. Finding definitive proof that life exists or once existed is extraordinarily challenging. Consider how much more difficult it would be to not only find life on a distant exoplanet, but also to piece together the entire story of its evolution. This leads us to definitions derived from the laws of thermodynamics. When physicists tackle a problem like defining life, their primary strategy is to drill down to the most fundamental laws of nature that govern the system in question, whatever it may be. This approach has been a cornerstone of science at least since Isaac Newton demonstrated that the movement of any object in the universe can be described by the three laws he formulated. As we mentioned in the previous chapter, one could say that the ultimate ambition of physics is to distill the rules of the universe's existence into a set of equations so simple they could fit on a t-shirt. From a physicist's point of view, understanding life on Earth begins with two fundamental concepts: energy and entropy. These principles fall under the purview of thermodynamics, a field of science that took shape during the 19th century. As we've previously touched upon, this science is governed by two primary laws, which can be summarized quite simply. The first law states that while energy can change from one form to another, it can never be created or destroyed. The second law posits that within any closed system, the level of disorder, known as entropy, will either stay the same or increase over time. It will never decrease. The second law is typically explained using the concept of entropy, which serves as a metric for a system's disorder. A state of high entropy signifies a great deal of chaos, whereas low entropy indicates a high level of order. A classic analogy used to explain thermodynamic principles is a teenager's room. Left unattended, the room naturally becomes messier, which means its disorder increases, or in scientific terms, it moves toward a state of higher entropy. You could say that this cluttered condition is the system's natural state of equilibrium. To combat this descent into chaos and maintain the room in a state far from equilibrium, constant cleaning is required. This tidying process demands an input of energy, which for the teenager, or more realistically their parents, comes from food. Once the cleaning is complete, the first law of thermodynamics dictates that this energy must be conserved. It is released into the surrounding environment as heat. Therefore, to sustain a highly ordered, low-entropy state, a continuous flow of energy must pass through the system. In the language of physics, this energy flow is what sustains a system in a highly organized condition, far from its equilibrium point. A living organism, such as your own body, is a perfect example of such a highly ordered system, much like that impeccably clean bedroom. If left to its own devices, the collection of atoms that make up your body would rapidly devolve into a disorganized heap of matter. It is the steady stream of energy, derived from food and originating ultimately from the sun, that keeps your body far from this state of equilibrium and prevents it from collapsing into atomic disarray. From all this, we might surmise that a living system is one that is kept far from equilibrium by a constant flow of energy. However, this is less a formal definition of life and more a crucial characteristic of any living thing, a property that suggests life might be possible. Logically speaking, this represents a necessary condition for life, but it is not a sufficient one. In other words, while every living thing needs an energy flow to preserve its highly organized structure, not every system with such a flow is actually alive. A perfect illustration of this is a growing snowflake. It is a highly ordered structure that utilizes thermal energy from its environment to expand, yet no one would consider it to be alive. This thermodynamic perspective on life will become incredibly valuable later on, when we explore the potential for life forms that are entirely different from anything we know. Shifting our focus to technology, a pivotal discovery was made in 1960 when paleontologists Lewis and Mary Leakey unearthed hominin fossils in Tanzania's Olduvai Gorge, surrounded by primitive stone tools. This particular hominin was given the name Homo habilis, or handyman, and is recognized as the first of our ancient relatives to manipulate objects in their environment to create tools, in this instance, by chipping away at stone fragments. With a brain approximately half the size of a modern human's, Homo habilis initiated the long journey of technological advancement that has culminated in our sophisticated society today. It was once thought that tool-making, alongside language, was a defining trait that separated humans from all other animals. We now recognize that the line between humans and other species is much less distinct than was once assumed. Many animals can be seen using rudimentary tools. Chimpanzees, for instance, are known to use sticks to fish termites out of their mounds for a meal. Of course, it would be unreasonable to suggest that a simple stick is in any way equivalent to something like a Boeing 747 airliner. The key distinction, as with many other human traits, is not the capability itself, but the incredible degree to which it is developed. Clearly, the capacity to transform materials from the environment into useful tools is a fundamental prerequisite for the development of any technological society. This brings up a fascinating point when we contemplate life on other worlds. Here on Earth, the abundance of different kinds of stone gave our ancestors the raw materials to craft ever more sophisticated implements. The same is true for metals that are easy to smelt, which are plentiful on or just below our planet's surface. Without them, we might never have advanced beyond the Stone Age. However, there is absolutely no guarantee that easily accessible materials for tool-making are a common feature on every exoplanet. Consider a world entirely covered in water, where rocks and metals might be incredibly rare. On such a planet, the emergence of what we would recognize as a technological civilization would be, at the very least, an immense challenge. This means that when we search for life on exoplanets, we should consider not just the presence of organisms, but also the availability of resources they could use to build a technological society. This brings us to the fundamental rules of the game and the question of how any living system ought to operate. It's a strange paradox that while defining life itself is incredibly difficult, perhaps even impossible, outlining the essential properties that life must have on distant worlds is a far more manageable challenge. This is because we have a solid grasp of how life, at least life as we know it, evolves and functions within its environment. Furthermore, as we will explore, the principles that govern life on our planet are likely applicable to most other forms of life, not just those based on carbon. To theorize about the principles governing hypothetical life across the galaxy, we must first grasp the rules that shaped it here. Since Earth provides our only known instance of life's emergence, we'll start by examining its development on our homeworld, before imagining how similar processes could occur under the alien conditions of exoplanets. To truly comprehend how life on Earth evolved into its current state, you must address two core questions, which require us to draw upon insights from numerous scientific disciplines. The initial question concerns the very origin of life. How did living matter arise from inanimate components? The second, which is more pertinent to our exploration of exoplanets, asks how the first living organisms gave rise to the incredible diversity and complexity we observe today. Fortunately, we possess a relatively solid grasp of how this latter process occurred on our own planet, providing a crucial foundation for our inquiry. Our current comprehension of life's progression is founded on Darwinian evolution through natural selection, a concept we touched upon in a previous discussion regarding NASA's definition of life. Before exploring life's origins, it's vital to recognize that terrestrial lifeforms are now extraordinarily intricate, a product of billions of years of development. The very first organism, which we can refer to as the last universal common ancestor, would have been vastly different from anything alive now, unimaginably primitive and possessing just a small portion of the characteristics found in modern cells. You will see that the sophisticated features of contemporary organisms were all added later through the mechanism of natural selection. In its earliest days, our planet was a molten sphere moving through the cosmos, lacking any real atmosphere, oceans, or, of course, life. The young Earth was continually struck by cosmic debris as it circled the sun, and these very impacts generated sufficient heat to maintain its molten surface. The essential question of life's origin can be stated quite simply. How did our planet go from this primordial state to one capable of supporting at least a single living entity? We work from the assumption that most terrestrial exoplanets, being small and rocky, began under comparable circumstances, allowing us to model their potential for life based on Earth's history. We theorize that gas giants like Jupiter or Saturn formed through a different process, which invites a discussion on whether life there could have arisen in a completely distinct manner, perhaps requiring cellular structures adapted for buoyancy. As the planet moved beyond its initial fiery phase, the first major development was its cooling, which allowed its surface to solidify into a rocky crust. Water, sourced both from the planet's interior and from icy comets and asteroids, began to collect in ocean basins, creating the necessary environment for life's emergence. Geological evidence, like zircon crystals that trap water, suggests that liquid water was prevalent on Earth as early as 4.2 billion years ago. The paleontological record points to life arising on Earth not long after the period of intense asteroid impacts concluded, certainly by 3.8 billion years ago. This means that if you could travel back to that time, you would find oceans filled with cyanobacteria, which are dense blue-green algae. Essentially, life established itself on our planet with remarkable speed, appearing almost the moment the environment became hospitable. This rapid emergence raises a fascinating possibility. Within the epoch known as the Late Heavy Bombardment, there were probably quiet intervals, potentially lasting for millions of years, free from major collisions. Any life that might have arisen during these lulls would have been utterly annihilated by the next significant impact. An event on the scale of the Chicxulub impactor, for instance, would have released enough energy to vaporize the oceans and transform the atmosphere into superheated steam for millennia, a cataclysm no primitive organism could endure. From what we can reconstruct, scenarios like this likely occurred multiple times in our planet's early history. This implies that our own microbial ancestors were not necessarily the first life to exist on Earth. They were merely the lineage that managed to endure the final, sterilizing asteroid impact and carry on evolving. It's plausible that life arose and was extinguished dozens of times, but the only evidence we possess is of the one strain that survived the last great cataclysm. The initial move towards life's genesis involved the creation of complex molecules built around carbon atoms. For a long time, it was believed that constructing the intricate carbon-based chains found in living things was a nearly impossible task. Consequently, up until the mid-20th century, most researchers stayed away from this field of study, as the scientific community largely considered the origin of life to be an overly complex issue, better suited for philosophy than for conventional science. Research into the beginnings of life was finally catalyzed by a pivotal experiment performed in 1952 in the basement of the chemistry department at the University of Chicago. There, Nobel Prize winner Harold Urey and his graduate student at the time, Stanley Miller, set out to simulate the environmental conditions presumed to exist on the primordial Earth. Their experimental design was straightforward, featuring a flask of water to act as the ocean and a heat source to represent the sun. It also included an electrical discharge to simulate lightning, and a gaseous mixture of water vapor, methane, hydrogen, and ammonia, which Miller and Urey theorized was a close match to Earth's primitive atmosphere. After activating the heat and electrical sparks, the researchers let the apparatus run continuously for several weeks. By the conclusion of the experiment, the water had transformed into a murky, dark reddish-brown liquid that, upon analysis, was found to contain amino acids. To appreciate the significance of this discovery, you need to understand the role of proteins, which are one of the most vital molecule types in living systems. Proteins are responsible for regulating chemical reactions in every organism on Earth, and they are constructed from amino acids. You can imagine a protein molecule as a long chain where each individual link is an amino acid. Therefore, what Miller and Urey had successfully shown was that natural forces could generate the fundamental building blocks of life from materials that were entirely non-living, but believed to be plentiful on the early Earth. This outcome had a monumental effect on how the origin of life was studied, largely because it moved the entire problem from the domain of philosophy into the practical realm of science. In the wave of experiments that followed Miller and Urey's work, researchers managed to produce nearly all the essential molecules found in living things, including fragments of DNA chains and even complex proteins. The fact that Miller and Urey's original assumptions about Earth's early atmosphere were later proven incorrect turned out to be surprisingly unimportant. Subsequent experiments that utilized different atmospheric compositions and various energy sources yielded broadly similar outcomes, although the quantities of molecules produced did change with each specific setup. Furthermore, complex organic molecules, amino acids included, have since been identified in meteorites, vast interstellar molecular clouds, and even within the debris disks around stars where new exoplanets are forming. This means that, contrary to what was once expected, the basic molecular components of life are actually quite widespread throughout the universe. With these building blocks proving to be so common, the primary question surrounding life's origin shifted to how these components could assemble into something we would undeniably recognize as living. A great number of theories have been put forth to account for this process, yet none has managed to achieve universal acceptance among scientists. At a minimum, however, we can draw one firm conclusion from Earth's own history. Regardless of how this assembly of non-living matter into living organisms took place, it must have happened remarkably fast. The idea of a primordial soup emerged from theories following the Miller-Urey experiment, which suggested that processes in Earth's early atmosphere would have resulted in continuous rains of organic molecules. These downpours would have transformed the planet's oceans into a dense organic broth. Calculations indicated this process could have been completed within a few 100,000 years, a blink of an eye in geological terms. Theorists then proposed that random collisions between these molecules would inevitably produce a chemical structure capable of absorbing materials and making copies of itself, which we now call the last universal common ancestor. This concept gained so much traction that the Smithsonian Institution even created a film where the renowned chef Julia Child was shown mixing a batch of primordial soup in her television kitchen. Soon after, several variations of the primordial soup scenario began to appear, each presenting a unique take on how this ancestor might have formed. Charles Darwin, for example, once mused that life could have begun in a warm little pond, a concept later developed by scientists who suggested that coastal pools filled with organic, rich water at high tide could have been the key. As this water evaporated, it would have left behind increasingly concentrated layers of organic molecules, creating the perfect conditions for a chance combination to spark the first living organism. In time, other models surfaced, each attempting to outline the specific conditions that might have aided the leap from simple building blocks to self-replicating cells. One hypothesis, for instance, proposed that electrical charges on the surfaces of clay deposits could have served as catalysts, igniting the initial chemical reactions essential for life. Other researchers imagined that every bubble in the ocean's foam, or alternatively, each droplet of fat in the soup, functioned as a tiny, independent chemical experiment containing a distinct mix of molecules. Another scenario posited that life first arose inside a rocky cavity near a deep-sea hydrothermal vent, a model that neatly eliminates the need for an early organism to have a cell wall or membrane, as the cavity itself would have performed that function. All of these models concerning the origin of life can be categorized as different versions of the frozen accident theory. The central premise is that countless random combinations of molecules were formed over and over until, through sheer coincidence, one of them turned out to be capable of self-replication. As soon as this occurred, the great wheel of life began to spin, and the process of natural selection kicked in. That first molecular combination became frozen, while all of its potential competitors were ultimately left behind in the evolutionary race. You could spend your whole life alongside a frozen accident without ever being aware of it. Just take a look at your computer keyboard. Do you notice the specific arrangement of the letters in the top row, which we know as QWERTY? That layout is a perfect example of a system that emerged from a series of historical chances and then became locked in, much like the first self-replicating molecule. The familiar QWERTY keyboard layout was created in the 19th century, specifically to prevent the keys of mechanical typewriters from jamming. This arrangement has persisted as a kind of historical accident. Even though our keyboards are now electronic, we continue to use this design because changing it would be an immense undertaking. In a similar vein, some theories proposed that the first cell, capable of replication, became the blueprint for all life that followed, not because it was the most efficient design, but simply because it was the first to exist. The Miller-Urey experiment unleashed a flood of new concepts and speculations regarding the origin of life. As researchers gained a deeper understanding of life's fundamental chemistry, two primary schools of thought emerged to lead the conversation. We can refer to these competing ideas as the RNA world hypothesis and the metabolism first theory. Let's start with the RNA world. The inner workings of modern cells are quite fascinating. For the chemical reactions essential to life to proceed, they rely on specialized molecules known as enzymes, which in all terrestrial life are proteins. This is precisely why the Miller-Urey results were so groundbreaking, as they demonstrated a plausible pathway for amino acids, the constituents of proteins, to form from inorganic matter. Yet, this presents a classic paradox. The information required to construct the amino acid chains that form proteins is stored within a complex molecule called DNA, and this information is relayed to the proteins through another intricate molecular system, RNA. The dilemma is that reading the DNA code in the first place requires proteins. This creates a circular dependency. You cannot build proteins without first decoding DNA, but you need proteins to carry out that decoding. This is a quintessential chicken and egg scenario. A potential answer to this puzzle emerged in the early 1980s, when researchers discovered that certain RNA molecules, which they named ribozymes, could function not only as messengers for DNA, but also as enzymes themselves. This finding gave rise to a new version of the frozen accident theory, suggesting that a proto-RNA molecule appeared randomly and served in the earliest life forms as both an enzyme and a part of the protein-building process. This concept, the RNA world hypothesis, is currently the most favored scientific explanation for how life began. The opposing perspective, which we have termed metabolism first, entirely dismisses the notion of a frozen accident. This theory suggests that the earliest living system, or protocell, contained neither DNA nor RNA at all. Instead, it sustained itself through a series of straightforward chemical reactions, catalyzed only by small molecules without the need for complex enzymes. It was only much later, guided by natural selection, that the sophisticated chemistry of the modern cell evolved. To help you visualize how this might have unfolded, imagine trying to explain the incredibly intricate system of federal highways in America. You wouldn't begin by analyzing the current roadmap and traffic patterns. A more logical approach would be to go back to the continent's earliest transportation networks, like primitive footpaths. From there, you could trace their gradual evolution into unpaved wagon trails, see how the first cars began to use them, and then follow the process as roads were paved and service stations appeared, eventually arriving at the complex system we see today, without any need for improbable, random events. So, which of these two possibilities, the RNA world or metabolism first, represents what truly happened in Earth's distant past? We still lack a definitive answer. It's even possible that both hypotheses are incorrect. What we can state for certain about life's emergence on our planet is that first, Earth possessed a rich supply of the essential molecular components for creating fully functional living systems. Second, regardless of how the first living organism was assembled, the process occurred rapidly. However life came to be on Earth, whether through one of the scenarios I've described, or by some other means entirely, it doesn't imply that life must arise the same way everywhere in the galaxy. Even on other worlds with oceans of liquid water, there could be dozens, hundreds, or even millions of different pathways to life. These worlds could feature entirely different molecules for storing genetic information, and different proteins to manage their chemical reactions. As we continue, you must be careful to avoid what could be called Earth chauvinism, the presumption that life across the cosmos must be a reflection of life on our own planet. Let's explore some of the ways these differences might manifest. Even life as we understand it, which is based on chemical reactions of carbon compounds within a liquid water medium, doesn't have to mirror what we're familiar with on Earth. Consider the structure of proteins, the molecules that serve as enzymes and regulate chemical processes in terrestrial organisms. As I mentioned, proteins are like chains made of smaller molecular links called amino acids. In scientific laboratories, researchers can synthesize many varieties of amino acids, and this is a vast and quickly expanding area of study, with non-natural proteins being used for everything from creating new medicines to manufacturing biodegradable plastics. Life on Earth is constructed from a surprisingly limited set of amino acids, just 20 or 22 based on the counting method. This raises an interesting question. Is this specific selection merely a historical fluke, a frozen accident from our planet's distant past? If that's the case, we could find extraterrestrial organisms with proteins built from entirely different amino acids, resulting in completely alien biochemistries. Alternatively, if our set of amino acids provided a crucial evolutionary edge, then it's conceivable that all carbon-based life across the universe shares a genetic code very much like our own. You can extend this line of questioning to nearly every chemical aspect of life on our planet, starting with its choice of solvent. While water is plentiful throughout the cosmos, is it truly indispensable for carbon-based life? Take Jupiter, for example, which is paradoxically the most arid location in our solar system, essentially a desert on a planetary scale. Information gathered by the Galileo probe confirms this, revealing that Jupiter's atmospheric water vapor content is as low as that found in sugar. Despite this dryness, we've observed that complex organic molecules like benzene form with ease in its atmosphere, powered by the sun's ultraviolet light. This discovery demonstrates that intricate molecules can arise even in environments with very little water, which makes you wonder if such a process could trigger chemistry akin to the Miller-Urey experiment and eventually give rise to life. We often default to the assumption that life requires water, both because it's our own experience and because water is an exceptional medium for chemical interactions. For molecules to react, they need the freedom to move and meet, a process far more efficient in a liquid state. However, it's crucial to remember that water isn't the only liquid the universe has to offer. Consider Saturn's moon Titan, where vast oceans of liquid ethane and methane exist. While chemical processes in such frigid conditions would be extraordinarily slow, who's to say that extraterrestrial life must operate on the same timescale as ours? On the opposite extreme, you could envision planets so intensely hot that their surfaces are covered in seas of molten magma. Although the molecules familiar to us would be destroyed in that heat, it's possible that completely different, more resilient molecules could thrive. It seems that whenever we contemplate life elsewhere, we find ourselves with far more questions than definitive answers. And what about the fundamental atoms themselves? The moment we begin to speculate about life that isn't based on carbon chemistry, the inquiries become exponentially more difficult. We have a solid understanding of how the fundamental components of carbon-based life either appeared or could theoretically appear. Yet the parallel questions of how life centered on other elements might begin and evolve remain almost entirely uncharted territory. It's not a stretch, though, to picture an alien researcher, perhaps a creature made of silicon, performing its own version of the Miller-Urey experiment to uncover the origins of its species. To truly entertain the possibility of life profoundly different from our own, you might need to look beyond molecular chemistry entirely. When exploring a concept like electromagnetic life, for instance, it's interesting to note our understanding of electric and magnetic fields is far more advanced than our grasp of molecular biochemistry. We've long understood the fundamental principles that moving charges produce magnetic fields, and shifting magnetic fields induce electric ones. But this deep knowledge might be completely inadequate for conceptualizing the intricate living systems that could emerge from such electromagnetic forces. Once the initial hurdle of life's origin is cleared and a self-replicating entity has formed, a completely different set of rules takes over, driving development at an accelerated pace. This idea connects directly to discussions about the definition of life and Darwin's theory of evolution. The focus now shifts to how this evolutionary process sculpted life on our own world, the powerful evidence that supports it, and why we believe these same evolutionary forces would likely be the main engine for life's progression on any other habitable planet. The entire case for natural selection rests upon two straightforward and undeniable observations. The first is that members of any given species display a range of different characteristics, and these characteristics are heritable, meaning they can be passed down to subsequent generations, often with random modifications like the DNA mutations we see on Earth. The second observation is that individuals within every species are in constant competition for the limited resources within their shared environment. Here on Earth, you can easily see that individuals of the same species possess distinct attributes. Certain rabbits are naturally faster runners, while the specific shape of a bird's beak might make it a more efficient forager. Similarly, some rams might achieve greater reproductive success than their rivals. When Charles Darwin first formulated his theory of evolution, he didn't understand the underlying mechanics of inheritance or the reasons for these variations. He simply observed the crucial facts, that individuals varied, and that their unique traits could be passed on to their offspring. A truly delightful part of reading Darwin's On the Origin of Species is delving into his meticulous accounts of pigeon breeding. You can almost picture him discussing the hobby for hours with fellow enthusiasts in a neighborhood pub, which he actually did. At the heart of his theory is a beautifully simple idea. Certain genes provide an organism with traits that improve its chances of surviving to reproduce. Consequently, those specific genes have a statistically greater probability of being transmitted to the next generation compared to others. Paleontologists refer to this phenomenon by saying that these advantageous genes are selected. With the passage of enough time, these selected genes grow to become dominant within the population. When this selection process is repeated over and over through countless generations, it ultimately leads to the formation of entirely new species. So, even though Darwin had no knowledge of genetics when he named his seminal work, he was, in essence, describing the origin of species through the inheritance of genes. Although Charles Darwin himself didn't coin the term survival of the fittest, it quickly became a popular summary of his theory. The crucial takeaway is that the meaning of fittest is entirely dictated by an organism's specific surroundings. For instance, in a habitat teeming with predators, a rabbit's speed is a key advantage for passing on its genes. But in an environment where food is scarce, superior traits like a heightened sense of smell might prove far more beneficial, demonstrating that fitness is never absolute, but always relative to the challenges of a particular setting. The incremental quality of evolutionary development brings up another critical point you must consider. When you envision how a creature adapts to its environment, it's essential to picture a slow, cumulative progression where every single stage provides a distinct survival advantage. To suggest that pigs would simply benefit from wings is not a valid evolutionary argument. Instead, you have to map out a plausible, step-by-step path where each modification improves the organism's chances, such as side protrusions, first regulating heat, then enabling gliding, and eventually becoming fully formed wings. This requirement to justify every developmental stage will be vital as we explore potential life on exoplanets. Before moving on, we also need to address the question of how quickly evolution actually happens. Two primary, opposing viewpoints exist on this subject. One is gradualism, which posits that significant shifts arise from the steady accumulation of minor alterations over time. The other is punctuated equilibrium, which proposes that species experience long stretches of stability interrupted by brief, intense periods of rapid change. Since all these developments stem from DNA modifications, you can see how both scenarios are genetically plausible. A mutation in a single gene might cause only a small change, supporting gradualism, whereas a mutation in a regulatory region of DNA that controls multiple genes could spark a cascade of major transformations, fitting the punctuated equilibrium model. In the end, the truth of how life evolved on Earth likely involves both gradual and sudden changes. Whether life on exoplanets would follow a similar dual pattern depends entirely on its method for passing traits to the next generation. Now, while countless pieces of evidence support the theory of evolution, I want to concentrate on two of the most compelling fields: the fossil record uncovered by paleontology and the data from modern DNA sequencing. Among the most striking fossil evidence are the petrified remains and skeletal imprints of animals that vanished long ago, which allow us to piece together the comprehensive history of life's progression. Every extinct species that you can find in the fossil record signifies another branch on the intricate tree of life. Beyond skeletons, we've also discovered fossilized plant matter and, more recently, the preserved remnants of single-celled life in ancient rock, a finding that helped us gauge the rapid pace at which life first emerged on our planet. Since DNA holds the complete blueprint for the organism it belongs to, our capacity to decode its sequences provides a second, powerful method for tracing life's history. The fundamental concept is straightforward. The more significant the genetic differences between any two species, the more distantly in the past their shared ancestor existed. By calculating the average rate of mutation, a technique referred to as the molecular clock, we can translate this genetic data into a detailed genealogical tree that maps out the evolutionary story of life on Earth. For me, the single most powerful confirmation of Darwin's theory is the remarkable fact that the family tree constructed from the fossil record aligns perfectly with the one derived from DNA analysis. This convergence of two independent lines of evidence is so strong that I believe Darwinian evolution deserves its place among the fundamental principles that govern our universe, right next to concepts like gravity. Natural selection is a universal force. It will unavoidably arise in any system where traits are inherited from one generation to the next, and where those traits are subject to change. For any form of life based on chemistry, be it carbon-based or something else, the environment will invariably present mutagens, like temperature fluctuations, ultraviolet light, and chemical interactions. Consequently, any given population will continuously produce individuals with traits that make them better suited to their surroundings than their peers, which is the only prerequisite needed to activate the engine of natural selection. This universality leads to the conclusion that evolutionary theory is the most logical starting point when you contemplate life on other worlds. But you must grasp this critical distinction. While natural selection will be the governing principle everywhere, the specific forms of life it sculpts will be incredibly diverse, shaped by unique environmental pressures. For instance, imagine life evolving in the upper atmosphere of a gas giant. Here, the power to regulate one's buoyancy would offer a tremendous advantage, enabling a creature to drift between atmospheric strata to hunt for sustenance, much like the flying dragon we envisioned. Consider, for instance, a planet in a state of synchronous rotation, a topic we'll explore in greater detail later. On such a world, the constant, ferocious winds sweeping across the surface would likely provide an evolutionary advantage to creatures that are low-slung and streamlined. In the discussions that follow, we will examine the unique conditions on various exoplanets to see how they might shape the course of natural selection for the hypothetical life forms we imagine there. However, I find it far more compelling to think about circumstances where the principles of natural selection might not even be relevant. Let's look at a couple of scenarios that illustrate this point. The first is a world with no individual organisms. Natural selection fundamentally relies on competition for resources among separate individuals. But what if life on an exoplanet existed not as distinct beings, but as a single, contiguous organism, spanning the entire globe? Here on Earth, the largest known living thing is a fungus in Oregon, Armillaria ostoyi, which is a single entity covering more than 3 kilometers. It isn't a great leap to envision a similar organism enveloping an entire planet. In such a case, with no individuals to compete against one another, would the mechanism of natural selection still have a role to play? The answer to that question requires some careful thought. This colossal fungus is composed of cells that divide as it expands, a process influenced by environmental conditions. Within a planet-sized organism, the fundamental processes of cellular growth and division would operate just as they do in smaller life forms. Therefore, should mutations arise in the cells of this giant creature, different sections of its body could adapt to their local surroundings in distinct ways. Natural selection, in this context, would act upon different parts of a single organism instead of on separate individuals of a species. The only way around this conclusion is to imagine that a complex, planet-sized organism could spontaneously materialize in a fully developed state. This idea, however, is so fantastically improbable that we can confidently set it aside. This brings me to another scenario: the perfect planet. The primary engine of natural selection on our world is the relentless change occurring on its surface, driven by processes deep within its core, forcing Earth's organisms to constantly adapt. The only way around this conclusion is to imagine that a complex, planet-sized organism could spontaneously materialize in a fully developed state. This idea, however, is so fantastically improbable that we can confidently set it aside. This brings me to another scenario: the perfect planet. The primary engine of natural selection on our world is the relentless change occurring on its surface, driven by processes deep within its core, forcing Earth's organisms to constantly adapt. But what if an exoplanet were different, remaining fundamentally unchanged for billions of years? If life emerged on such a stable world, what we might call a perfect planet, it would evolve under the guidance of natural selection until it achieved a state of equilibrium with its environment. At that point, all evolutionary pressure would cease. While mutations would continue to occur at their normal rate, none could possibly improve life's adaptation to this perfect world, and they would eventually fade away, leading to a state of complete biological stagnation. A similar phenomenon is sometimes visible right here on Earth. The German geneticist Richard Goldschmidt referred to the results of mutation as hopeful monsters, most of which have no bearing on an organism's survival and vanish after a few generations. It's easy to project this concept to a point where these hopeful monsters disappear entirely. This is precisely what life would resemble on a perfect planet, assuming such a place could exist. I share these two examples with you as a form of caution. As we begin our search for life throughout the galaxy, we must be prepared to meticulously and repeatedly reevaluate nearly every biological rule we take for granted, and we must resist the temptation to jump to conclusions. This is simply the reality of how the universe operates. Our only choice is to accept this fact and work within its framework. This brings us to the question, is anyone else out there? Mars consistently ranks first on the list of celestial bodies where finding evidence of living organisms seems most attainable. Over the last 50 years, a veritable fleet of spacecraft has journeyed to the Red Planet. Landers have successfully touched down in dozens of locations, and at this very moment, the Curiosity rover is ascending a mountain near the Martian equator, a place of immense geological significance. You would think that by now we would have a definitive answer as to whether life currently exists on Mars, or ever did. Yet, that is simply not the situation. Ever since 1976, when the Viking landers became the first human-made craft to land on Mars, the scientific community has been mired in a slow-moving debate over whether the data they collected confirms or denies the presence of life there. The importance of this debate is difficult to overstate. Unless we manage to invent something like the warp drive from Star Trek in the near future, it is highly improbable that we will ever investigate another planet with the same thoroughness we have applied to Mars. So, if after half a century of intensive exploration we still cannot be certain about life on our celestial neighbor, what hope do we have of answering that same question for a planet that is light years away? The search for life on Mars has been, without any exaggeration, a chronicle of disappointments. Time and time again we have encountered phenomena that appeared to be clear indicators of biological processes, only to discover later that they could be explained just as well by ordinary chemical reactions. We continue to accumulate more clues, but a conclusive answer remains elusive, leaving us with little more than frustration. Let's revisit the Martian Chronicles. In 1976, two Viking landers made successful touchdowns at separate sites on Mars. Each was equipped with the necessary hardware to perform 4 distinct experiments designed to detect signs of life. These experiments involved a molecular analysis using a gas chromatograph mass spectrometer and a gas exchange experiment, where Martian soil was combined with water and nutrients to monitor for any biological response. Another test was the pyrolytic release experiment, in which Martian soil was exposed to gases containing carbon, and then heated to check for evidence of photosynthesis. Finally, there was the labeled release experiment, which we will examine more closely later. The outcomes of the first 3 experiments were completely unambiguous. No evidence of biological activity was observed. In fact, the instruments failed to detect any organic molecules at all. It is critical to remember, however, that all of these experiments were conceived with a major assumption in mind: that any potential Martian life would possess a metabolism similar to that of life on Earth. As we've previously considered, this is a presupposition that may or may not be correct, fundamentally shaping how we interpret the results. Furthermore, these experiments were constrained to analyzing just the very surface of the Martian soil, probing no more than about 2 centimeters deep. Despite this limitation, it was the labeled release experiment that captured the most attention, igniting controversies that have endured for decades. The procedure involved placing a soil sample into a chamber where it was mixed with both water and a nutrient solution. These nutrients were specially prepared with a high concentration of carbon-14, a heavy isotope, rather than the standard carbon-12. While carbon-14 reacts chemically in much the same way as its lighter counterpart, its radioactivity makes it far easier to track. The underlying principle of the test was straightforward. If any microbes existed in the Martian soil, they would consume the nutrients and, in the process, release radioactive carbon dioxide gas that could be monitored within the chamber. And, amazingly, both Viking landers did indeed register the presence of this labeled carbon dioxide. However, the initial thrill generated by these published findings was short-lived. When the nutrient solution was introduced into the chamber for a second and then a third time, no further traces of the radioactive gas were found. Scientists deduced that if microbial metabolism had been responsible for the initial gas release, the microbe population should have expanded, leading to an even greater release of gas with each subsequent feeding. In contrast, if the gas was the byproduct of a non-biological chemical reaction, the initial reactants would have been used up, preventing the reaction from occurring again. The latter scenario is precisely what the data showed. Consequently, the consensus at the time, which still largely holds today, was that the Viking landers had not discovered conclusive proof of life on Mars, and later experiments even pinpointed the likely chemical reactions in the soil that could have produced this result. Yet, that is not where the narrative concludes. Since 1976, a small but very vocal contingent of scientists has maintained that the Viking data, when interpreted differently, actually serves as confirmation of microscopic life on the red planet. This enduring disagreement was vividly illustrated at a major NASA conference on extraterrestrial life in 2016, where the question and answer period following a presentation became almost entirely consumed by an intense and at times contentious debate over the Viking mission's outcomes. The conviction that life on Mars could still be found doesn't rest solely on the Viking results, however. As far back as 1971, the Mariner spacecraft, while orbiting Mars, transmitted images of the surface that astonished scientists, with their striking similarity to Earth's own river systems. In the years since, a multitude of orbital missions have furnished definitive proof that liquid water once carved paths across the planet. During its early history, Mars even featured a large ocean in its northern hemisphere, adding to the evidence of a once hospitable world. This watery past occurred at roughly the same time that life was first emerging on Earth, which lent widespread credibility to the notion that life might have also thrived on an ancient Mars. Proponents of this idea argued that even if that life vanished as the planet lost its oceans and atmosphere, we might still be able to discover its fossilized evidence. There is, however, a key Martian characteristic that gives scientists pause about the potential for finding preserved organic molecules: the planet's absence of a magnetic field. Without a protective magnetic field, the surface of Mars is perpetually bombarded by harsh solar radiation, which creates high levels of hydrogen peroxide, a potent sterilizing agent. This means the Martian surface is in a state of constant disinfection, which would destroy any organic molecules left behind by hypothetical ancient organisms. And yet, in 2018, a breakthrough occurred when the Curiosity rover found organic molecules within rocks that had formed when Mars was still a water-rich planet. While these molecules are not thought to be from currently living things, their very existence offers hope that biological signatures from the distant past could indeed survive to this day. But what about the possibility of life on Mars right now? You have to remember that we have only analyzed samples from the uppermost layer of the planet's surface, never digging more than a few inches down. It's fair to wonder if something vital might be concealed at greater depths. As the Curiosity rover made its journey through Martian canyons, the Mars Reconnaissance Orbiter captured images of dark lines on the surface that appeared to change with the seasons. One theory was that these streaks were formed by sudden flows of briny water seeping up from the Martian interior, though some scientists now propose they could be caused by shifting sand instead. Furthermore, in 2018, an analysis of data from the Mars Express orbiter led scientists to suggest the existence of a liquid water lake buried beneath the planet's northern pole. The presence of liquid water, even if it's deep underground, naturally prompts the question of whether microscopic life could also be present there. This presents yet another fascinating possibility for exploration. And on top of all this, we have detected methane on Mars. The methane molecule is quite simple, consisting of one carbon atom attached to 4 hydrogen atoms. Here on Earth, we know methane as the natural gas used for heating and power, and it exists in our atmosphere in trace amounts, about 1.8 parts per million, or roughly 0.18%. Critically, around 95% of the methane in Earth's atmosphere is generated by microbial life, although it can also be produced by non-biological processes, such as the interaction of groundwater with magma, or the much slower transformation of iron oxide into other minerals. In 2003, using ground-based telescopes and spectroscopic analysis, astronomers first detected methane in the Martian atmosphere. The quantity was minuscule, just 10 parts per billion by volume, significantly less than on Earth, but its existence was confirmed. Then, in a perplexing turn of events spanning late 2013 and early 2014, the Curiosity rover observed something extraordinary. As it navigated the Martian landscape, the concentration of methane in the atmosphere abruptly spiked, increasing tenfold for reasons that remain a mystery. After only a couple of months, the methane levels subsided to their usual state, leaving scientists to puzzle over the cause of this peculiar occurrence. This event, dubbed a methane spike, might have been a simple release of a trapped gas bubble from ordinary geological processes. However, an equally plausible explanation is that the spike was caused by a sudden bloom in the population of microbes living beneath the Martian surface, which once again offers an intriguing but inconclusive piece of evidence for life on Mars. This brings us to the remarkable story of a meteorite designated ALH 84001, which begins in the Allen Hills of Antarctica. This remote location, situated about 200 kilometers south of the McMurdo Sound Base, is a vast expanse of ice fields and slow-moving glaciers. When you're there, surrounded by this desolate landscape, you might wonder why anyone would ever visit such a place. But the answer is quite straightforward. It's a prime location for finding meteorites. The reason for this is a unique natural process. When a meteorite strikes the glacier in the Allen Hills, it becomes embedded deep within the ice and is carried along by the glacier's flow. As the ice pushes up against the slopes of the hills, powerful winds strip away the surface layers in a process known as ablation, exposing the meteorite. In essence, the entire ice field functions as a massive conveyor belt, collecting fallen space rocks and bringing them directly to the surface for discovery. It was here in 1984 that a team of scientists on snowmobiles came across a particular meteorite. This specimen was rather unremarkable at first glance, roughly the size of a grapefruit, weighing about 1.8 kilograms, and coated in a dark fusion crust from its fiery descent through our atmosphere. It received the designation ALH 84001 for Allen Hill's 1984 sample number 1, and was promptly boxed up and left in a lab, forgotten for almost 10 years. When researchers finally examined the rock in the mid-1990s, they realized they had found something extraordinary. Gas bubbles trapped within the stone perfectly matched the atmospheric composition of Mars, confirming its origin. Though this alone was not unique, as over 100 such Martian fragments have been found on Earth. What made ALH 84001 so special was its incredible age. Radiometric dating revealed it had formed 4 billion years ago, during a period when Mars was wet. Its journey involved being blasted from the Martian surface 17 million years ago, drifting through space, and finally landing in Antarctica about 13,000 years ago, making it a silent witness from an era when Mars might have harbored life. Then, in 1996, the story took a dramatic turn when a NASA team headed by astronomer David McKay announced a breathtaking discovery. After intensive study of ALH 84001, they asserted that the meteorite held the fossilized remnants of ancient Martian life. Their conclusion rested on 4 key pieces of evidence: the detection of organic molecules known as polycyclic aromatic hydrocarbons, or PAHs, mineral structures that looked like fossilized microbes from Earth, mineral combinations consistent with those produced by terrestrial bacteria, and finally, chains of magnetite crystals similar to those used by certain Earth-based microbes. The effect of this proclamation on both the scientific community and the general public was immense and cannot be overstated. It even captured the interest of the sitting U.S. President, Bill Clinton, and is widely credited with helping to launch NASA's astrobiology program, which continues its work to this day. But as time went on, McKay's team encountered significant scientific scrutiny, with critics pointing out that PAHs are actually quite common throughout the cosmos, having been found in comets and interstellar dust clouds where life does not exist. Regarding the shapes that resembled Earth fossils, skeptics observed that certain non-biological mineral formations on our own planet can look strikingly similar to cells. Furthermore, the supposed biological structures within the meteorite were roughly 100 times smaller than any known cells on Earth, leading to the speculative idea that they could be a new life form called nanobacteria, a concept that is theoretically possible but has never been observed. To cast further doubt, it was proposed that some of the specific mineral arrangements could have been created accidentally during the process of preparing the samples for analysis under an electron microscope. For a while, the most compelling evidence supporting the Martian fossil claim was the presence of magnetite chains. On Earth, certain bacteria use these chains as an internal compass to orient themselves, a tool that would have also been useful on ancient Mars when it likely had a magnetic field. This argument was compelling, until other scientists showed that similar magnetite crystals could be produced through entirely non-biological means, specifically during the extreme heating the meteorite experienced while plunging through Earth's atmosphere. In the end, we were right back where we started, with inconclusive data. The structures inside ALH 84001 could be genuine Martian fossils, or they could simply be the product of ordinary geology and chemistry. After all this effort, we still couldn't make a definitive statement about life on Mars, past or present. This leads to a daunting question. If we can't be sure about our next-door neighbor, how could you possibly hope to find life on distant, unreachable exoplanets? The answer may lie in a final hope called spectroscopy, a technique whose potential is highlighted by a story from the early 19th century involving the French philosopher Auguste Comte, who once famously declared that we would never discover the chemical makeup of the stars. Auguste Comte's logic was straightforward. In his era, the only method for determining a substance's chemical makeup was through direct laboratory analysis. He famously argued that because we could never bring a piece of a star into a lab, we would forever remain ignorant of their composition. One can easily surmise his view on exoplanets would have been identical, believing that their unreachable nature meant their chemistry would always be a mystery. However, this entire paradigm was upended in 1859 when two German scientists, each distinguished in completely different disciplines, collaborated in a Heidelberg laboratory. Gustav Kirchhoff, a name familiar to physics students for his work on electrical circuits, and Robert Bunsen, creator of the indispensable Bunsen burner, embarked on a series of experiments that would transform our ability to study the universe. Their procedure involved passing light from a heated, pure substance through a glass prism, which separated the light into its constituent colors. Instead of the continuous rainbow they anticipated, they discovered that every chemical element generated a distinct and clearly defined pattern of colors. This unique combination of colors is what we recognize today as an emission spectrum, which has a counterpart known as an absorption spectrum, relating to how photons of specific energies are absorbed. The scientific field devoted to analyzing these patterns is called spectroscopy. You are likely already acquainted with the core principle that various chemical elements emit light of different colors. For example, you have probably observed the distinct yellowish hue of certain streetlights, which are sodium lamps. They are often used in foggy regions because their specific wavelength of light penetrates the haze more effectively. Since every element produces a particular set of colors, this optical fingerprint allows us to definitively identify that element in any light source. A remarkable aspect of spectroscopic analysis is its indifference to distance. Whether the light source is a mere few centimeters away or separated by billions of light years, it makes no difference. Once this spectroscopic fingerprint is imprinted onto a beam of light, it travels with it indefinitely. Interestingly, while a modern spectroscope might be a computerized device costing tens or even hundreds of thousands of dollars, Kirchhoff and Bunsen successfully constructed their first one using only cigar boxes and a pair of old eyeglass lenses. It wasn't until the early 20th century that the scientists developing the new field of quantum mechanics could finally explain the mechanism behind these atomic spectra. Their understanding was facilitated by a simplified atomic model, which revealed that electrons cannot orbit a nucleus at any arbitrary distance, unlike planets around the Sun. Instead, they are confined to specific, discrete paths known as allowed orbits or orbitals. Each of these electron orbits corresponds to a precise energy level. An atom either emits or absorbs a specific quantity of radiation when an electron shifts from one orbit to another, with the amount of radiation matching the energy difference between the two levels. If an electron moves closer to the nucleus, radiation is emitted. If it moves farther away, radiation is absorbed. Because the atoms of each chemical element possess a unique configuration of orbitals, they each produce a unique spectrum of colors. Spectra are not exclusive to individual atoms. Any system with differing energy levels can generate such a characteristic fingerprint. For instance, complex molecules are capable of vibrating, rotating, and altering their geometric shapes, and each of these states yields a distinctive spectrum. This makes spectroscopy an ideal method for hunting for the molecular signs of life on faraway exoplanets, as detecting these biological molecules in their spectra would offer definitive proof. Consider our own planet as an illustration. The existence of life on Earth has a profound effect on the chemical makeup of our atmosphere. In fact, of the hundreds of gases present, very few are untouched by the influence of living organisms. Helium, constituting about 1% of the air, is a relic from the Big Bang, while argon, found in even smaller traces, results from the radioactive decay of potassium deep within the Earth. Virtually all other gases in our atmosphere are produced, consumed, or modified by biological activity. Photosynthesis in plants generates the oxygen we depend on, converting water and carbon dioxide into carbohydrates with the help of sunlight. This molecular oxygen is then broken down by solar ultraviolet radiation into individual oxygen atoms, which recombine to form ozone. In turn, respiration and decomposition release carbon dioxide, essentially reversing the photosynthetic process. Other atmospheric gases, like hydrogen sulfide, are byproducts of cyanobacteria, while certain other bacteria, as noted before, are responsible for releasing methane. Earth's atmosphere is therefore unmistakably imprinted with the evidence of life. These traces are what we refer to as chemical markers or biosignatures, and they offer a potential roadmap for finding life elsewhere. Given this, one might assume it would be a simple task to use spectroscopic techniques to scan the atmospheres of exoplanets for these biosignatures. However, the reality is far more complex, and we are confronted with three significant challenges. The first of these problems is the extreme faintness of exoplanets. We can only see them by the starlight they reflect. Simply detecting that minuscule amount of reflected light across the vast distances that separate us from even the nearest stars is a monumental technical hurdle. Even so, astronomers have recently developed the ability to analyze the light emanating from numerous exoplanets, employing highly sensitive instruments and sophisticated observational techniques. The most successful method involves a two-step process. First, you measure the light from the parent star while the planet is concealed behind it. Next, you measure the combined light from both the star and the exoplanet when it passes in front. By subtracting the first reading from the second, you can isolate the characteristics of the exoplanet's own light, effectively revealing its spectrum. The second major challenge lies in identifying the signatures of specific molecules within that exoplanetary spectrum. Although every element and molecule possesses a distinct light-based fingerprint, the portion of the spectrum that serves as a unique biomarker often represents a tiny fraction of the planet's total light. This reality means you must gather the maximum possible amount of light from the exoplanet, a task that generally demands the power of enormous telescopes. A third problem proves even more complex than the first two. How can you definitively determine which biomarkers are true indicators of life on an exoplanet? As we've discussed, living organisms produce or modify most of the gases in Earth's atmosphere. It might seem logical, then, to simply search for these same gases in the atmospheres of planets around distant stars. However, the situation is not nearly that simple. The difficulty is that nearly every molecule in our atmosphere that you might label a biomarker can also be created through non-biological means. Consider oxygen, for example. Ultraviolet light from the sun can split atmospheric water molecules, freeing oxygen atoms that later form molecular oxygen. While photosynthesis accounts for the vast majority of our oxygen, it isn't the only source. The same principle applies to methane, which, as I've noted, can be produced in many ways that have nothing to do with biology. This also holds true for hydrogen sulfide, with its signature rotten egg smell, which is generated by certain bacteria on Earth but is also expelled during various volcanic events. The list of such examples is extensive, but the main point should be clear. Practically every molecule you might propose as a biomarker for life has non-biological formation pathways in addition to biological ones. Some scientists therefore suggest that you should look for combinations of molecules that are produced by life. Take oxygen and methane. Methane is unstable in Earth's atmosphere and quickly oxidizes, but its constant presence is maintained by biological production. If all life on our planet were to end, the methane would vanish in a few decades, while the oxygen would persist for millennia before being absorbed by minerals. Consequently, the simultaneous presence of both gases could serve as a powerful biomarker, even if each one individually tells you very little. Ultimately, discovering biomarkers on exoplanets is a far more difficult endeavor than just looking for the gases produced by life on Earth. This is a field of research that is actively evolving and remains a subject of vigorous debate among scientists. The current, provisional conclusion from these discussions is this: you cannot confidently assert that you've found signs of life on an exoplanet based solely on the spectral lines of individual atoms and molecules in its atmosphere. The most promising strategy for such a search appears to be identifying specific combinations of gases that are generated by biological activity. So, let's briefly summarize what we've established. We now understand that life on almost any exoplanet must arise through natural selection, a process of Darwinian evolution. We've also seen just how profoundly difficult it is to uncover truly irrefutable proof that life actually exists on these worlds. For now, however, let's set this particular problem aside and turn our attention to how the laws of natural selection might function under the incredibly diverse conditions found on the many different exoplanets we know about. This brings us to what can be called the study of imaginary life. In the upcoming chapters, I will present a collection of short, speculative essays that describe how a human, properly protected and equipped with highly sensitive instruments, might perceive the environmental conditions on a range of exoplanets if they were to visit. I've chosen this method of exploring new planets for one straightforward reason. As has been repeatedly stressed, terrestrial life is currently the only kind of life we know. Furthermore, humans are the only species whose reactions to new environments you can reasonably predict. With this understanding, let us finally embark on a journey to a world I will call Iceheim, the realm of ice.